Hey everyone, maybe this is your first time seeing me. My name's Dan. I'm one of the machine learning and developer relations engineers at Voxel 51. Today we're going to be talking about a pretty niche category of visual AI here with RGB-X model developments. So if you're not familiar with what a RGB-X model is, that X there is a placeholder for any four-channel type of model development. We're going to explain kind of what that is in our talk as we go through. And there's a lot of exciting development happening in this field, and it's kind of booming as of recent about the potential applications that actually could happen here. So I'm excited to bring you this talk. Once again, if you have any questions along the way, just drop those into the Q&A widget. I'll get them all at the end and answer any questions we might have. One of the things, as we have time going on here, of course, we have a lot of stagnation fears in general across all of AI. But we haven't really seen that in visual AI, right? There's a lot of people concerned about, LLM developments and, ChatGPT or OpenAI's newest models haven't been that great compared to previous improvements and such. But we're not seeing that in visual AI, right? We see a lot of the great new visual AI models coming out are still, groundbreaking, and the new tools and developments that are happening are completely revolutionizing how we're doing our business today, right? For example, just take SAM2, which is this video on the right, is a giant step forward for us on how we can do auto segmentations and even just how we think about videos in general. That doesn't take away the fact that 2024 is very clearly just a year of scaling in visual AI. We're taking a lot of steps to try to connect to our clouds, secure GPUs, and build out your stacks, right? In the past, it was all about writing great papers and proof of concepts. But now we're seeing a lot more application-focused work and a lot of tools, companies, and startups helping us build out our AI stacks. I'm sure you probably recognize a lot of these logos, and probably if you're in visual AI, you've been familiarizing yourself with them over the past year or two. However, we're going to be talking about RGB-X models, right? So here is a little bit clip from the newest meta model, Sapiens, which is kind of very timely for giving this talk, of showing what is possible with these RGB-X models. So with RGB-X models, some of the most popular ones that we see are things like segmentation, depth, or normal, where outside of the regular red, green, blue that you store on your images, you can actually store whatever information you like in that fourth channel that's available for PNGs or in newer locations, just another way to overlay your images and store this fourth channel there. So we're going to be focusing on this specific topic and what it looks like today in visual AI. So what is an RGB-X model when we're talking about this? I've heard a couple other names about what this might be, but it seems like the industry is moving towards RGB-X. And it's basically any model designed to either input or output to four channels, right? A lot of times these models are used in unison with each other. It depends on the downstream use case here. So you might have use cases like we have down here on the bottom right, where we have infrared coming into our model, and we can actually boost things like object detection or segmentation by using infrared cameras at night. But we also have cases like we see in the top right and the bottom left, where I'm very interested in calculating the depth of my image for another potential downstream task. So I'm going to input a normal RGB image, and then I'm going to add this extra layer of information that is depth or surface normals or segmentations for some downstream task. This can be utilized across all different industries. I've been fortunate enough to experience this in many different fields, from things like law enforcement and disaster relief, using infrared to look through smoke to find people that are stuck in forest fires or other disasters, but also things like people in retail for virtual try-ons are very interested in this, 3D self-driving cars, in real estate. It's really all across all industries that is interested in these RGB-X models. However, I want everyone, as we go through this presentation, to kind of ask themselves, why does this work matter, right? There's so many cool models out there. There's so many really powerful visual AI models out there today. We look at VLMs and VQA, and now we have text-to-image generation, and now we can do all these awesome things with diffusion models. Why does this specific niche of visual AI matter, right? So keep on asking yourself, does this matter? Why is it important? And we're going to address this at the end of our talk after we kind of look at some of the previous and current works going on. So let's talk about some of the ways RGB-X models are being used today in production. The number one use case that we'll find across all different industries for RGB-X models is tracking. And when I say tracking, I mean your classic, there's person one and there's person two, and I watch a video stream, and I'm able to keep track of all these different people throughout my video stream, right? This is a classic extension of traditional object detection models. And the reasoning behind why tracking is so strong in the RGB-X field is because you're giving the model, the tracker here, more information to help make its decisions. So down here, we can see an example where this type of RGB tracker takes in any type of RGB-X. It can be infrared, depth, normals, any combination of those. And basically what you can see is that you just get higher accuracy whenever you add more of these kind of information to the model. Makes sense, right? With more data, more information, the model can make more accurate decisions. One of the really cool use cases, I've done this before, is there's this problem where you have night vision goggles and you want to be able to detect any type of object in night vision, right? This could be for a self-driving car. This could be on goggles. You can be, like I said, disaster rescue and things like that. However, there's certain times a day and certain locations that you might be approaching when you're wearing night vision goggles where normal vision is not good enough and night vision is also not good enough. And you kind of need to blend the two together, right? If it's not completely dark, right, there's maybe a light in the distance or something like that, that's going to make the night vision very hard to work with. The same way, though, it's still very dark and I can't see anything else around that light. So how can I get the best of both worlds? And this has been a focus of study for many years, not just recently, when it comes to RGB-X models and tracking, right? So we have a lot of work that we're seeing in kind of blending these two. They're using models like UNet to actually do like a blended vision of multiple modalities, or as we see in this use case, that we're actually just using a shallow embedding and prompting of RGB-X, the additional channels to kind of help our RGB tracker make these kind of decisions with multimodality aware inputs. One of the other really classic ways that this is being done today in production is surveying difficult terrain, right? The absolute classic use case here is some really hard or some area you really just don't want to go to, right? Think about things like if you want to do a structural integrity check of a nuclear reactor. Well, I'm not going to go have, the engineer go dive down the nuclear reactor. That sounds pretty dangerous for him. So what we do is you can fly some cheap drone with a couple cameras on it, fly the drone down. It does a 360 and it's going to get information like not just the RGB video, but it's going to get things like depth. Maybe it has LiDAR on it. Maybe it has thermal cameras or surface normals, event cameras, right? On this, and then you're going to be able to then project this 2D video into a 3D scene. You can then scan for any structural faults, see if there's any cracks. You can do this for interiors as well, or as well as like in terms of military or police activity. You can do this very quickly to get like a 3D scan of the active field you're going to go into, right? So if there's ever something like a SWAT location or something like that, this is being done today where they'll fly a drone through. And then on the iPad or wherever your downstream application is, you'll get a 3D projection of the scene so you kind of know what you're working with in case you're not familiar with the scene, right? So it's all about helping us quickly survey land and kind of use these additional inputs to give us a better 3D projection into what is actually happening here. And then the latest one within the last month is Meta's Sapiens model. Now, if you haven't heard about this model, I really encourage you to check out the paper and see what they've done. They did a really interesting work here where they tried to tackle a new area that they have never explored before, or any other really large company with large resources has explored before, which is trying to become best in class at a very specific task that does RGB-X tasks. So in this case, we have things like pose estimation, segmentation, depth, and normals. And Meta was able to get state-of-the-art in all four categories very, very easily, right? It's almost like 25% better than the previous model. Why is that the case? Long story short, a lot of it is I threw 1,000 GPUs at the problem, and lo and behold, I'm better than the rest, right? That's an easy way to look at the problem, and that does contribute to a lot of the state of the art, of course. However, they also took very unique approaches to how they were doing these works, right? Namely, it's only on humans. It's only a human-centric task. They actually put into the loss functions to not pay attention to any other loss other than ones that are humans. So if before every training run and anything like that, they specifically segmented the person out using like a detection or a segmentation model and said, okay, we're only going to train on this, right? We don't care about where they are, what location they are, anything like that. The model only trains to get better at human-centric pose, segmentation, depth, or normals. On top of that, they took a lot of other advancements, such as having some of the most advanced key point annotations, and then due to that, model outputs that has been available in the field before. The segmentation, if you kind of watch through these videos, is as advanced as ever before in the field, where we're doing things like top lip versus bottom lip, left arm versus right arm, right? Where we just weren't taking these things into consideration before because of either a lack of data that was this high quality, or because we didn't have models that were strong enough to accurately predict on them. Meta was able to conquer both of these problems pretty easily, it seems, by having a way farther ahead state of the art. And even when you compare it to its predecessors that are maybe only segmenting smaller parts of the body or less number of things, they're still blown out of the water. This follows as well for depth and normals. And it's very interesting because you can see that the clear use case here for Meta is most likely going to be Instagram play right now, where it's easier for me to put Instagram filters or anything like that on top of a person if I have such a smart understanding of the person. Right now, I know where their fingers are, their eyeballs are, the normals, the depths, the segmentations, and it just makes it a lot easier for that social media aspect of things whenever you want to apply AI models on social media. So like I said, really super cool paper. You should definitely check it out. I actually have a quick example of what that can look like if you want to run it yourself. So here's me at a very nice and beautiful Japanese garden. You can start by doing a prediction. You're going to have to tell Sapiens where the human you're interested is located. So we do a quick YellowBee8 prediction on top of our sample. From there, we can actually look at all the other different depths and stuff that we add to our image. So we have pose. You can see all the different pose points that were labeled on top. We have normals, where you can see it's getting all the different surfaces. You can see all the wrinkles in my t-shirt that it caught. Very high accuracy here whenever it does that. As well as segmentation. You can see it even gets my arms, the different parts of my elbow, the top lip, the bottom lip, my hair, my t-shirt. It even gets a little bit of clips of my pants that my pocket is in. As well as our depth map, right, where we can see the hot and cold and the different depths of your body. And so with 51, you can actually hold all these different RGB-X layers on top and kind of compare and contrast and be able to load these all into one sample. As we kind of begin to extend in computer vision, where RGB-X was typically held in the fourth channel of a PNG, well, now we can kind of go past that, and we can use tools like 51 to be able to have RGB-X be as many X's as you want on top of your samples. So that was just using the Sapiens model on Hugging Face. If you also want to get started with some other demos that we have a really good monocular depth estimation demo, which is an RGB-X model on our website, as well as there's tons of models to play with on Hugging Face spaces, such as the Sapiens model that I just pointed to. However, this is a great time to kind of revisit the why. Why is this important, right? Why is this, why are we making these models? Why are we seeing so much investment from companies like Meta now into these models? Is it really just to survey or search and rescue or social media? Because in a vacuum, none of these use cases move the needle, right? None of these use cases are groundbreaking. They don't seem to have a large increase over previous works. Even the things like social media filters, right? Like Snapchat's been doing filters for years, right? And they're pretty good. And sure, they're going to get better over time, but I highly doubt that someone like Meta is so invested in their Snapchat filters or filters that they're going to be investing all this GPU time to try to build a state-of-the-art model to have the best Instagram filters, right? It's just not likely. So why is this work important? And the answer here is we need to look to the future, right? We need to think about what is the 5, 6, 7 year plan here, and how do these RGB-X models fit into that plan as well? So very quickly, just thought process, right? We've been talking about how it's all about more information, right? We looked about at the RGB-X tracker that the accuracy gets so much better whenever we pass in these other modalities, right? That's what we were talking about earlier. And so maybe I don't have those modalities on hand, right? I don't have a thermal camera on me at all times, or an event camera, or, I do have a LiDAR camera. I just have my iPhone, right? So that one works, but the other ones, you just don't have them, right? And in some cases, it won't work, right? And in this case, if I have satellite imagery, I hope the satellite doesn't have an iPhone on it. But if you were going to pass a downstream task into a model, which do you think would give the model more information? This 2D satellite imagery of an aerial view, or a 3D rendering of the space with colors and textures and surfaces, and having absolute knowledge of how the space is laid out, and having distances and actual metric distances, right? So it's all about helping us try to get more information into another model, right? We can think about this the same way with our Sapiens model, right? Now, if I have some downstream task, right? Sure, it could be filters, but think about all the downstream tasks we could have for human-centric tasks, where previously I only had this image to work with. Now, instead of having only this image to work with, some downstream model that may or may not exist today now has pose estimation, it has segmentation understanding, it has depth understanding, it has normals understanding. And so whenever we get to that next task, we're going to have so much more information to give our model to feed into that. And so, what does this mean for machine learning? We have three main points here, and they kind of step up with how serious they mean, right? And the first one very easily is search, right? This could be done tomorrow, right? Where now I can search distances of key points. I can search based on depth. We have embeddings for all of these things. So now I'm no longer just doing your classic clip embeddings with text and image, but now I can actually have embeddings for depth. I can have embeddings for key points. I can have embeddings for my normals and stuff like that. So I can say things like, show me all my images where the person is really far away. Show me all my images where the person's knees are not shown, right? I only want torso up images or something like that. Where we didn't really have good context into this before, now we do, right? And this is going to empower our next kind of data set creations, our next data set curations, and help us build better data sets, help us find the samples we're looking for to help build that next task. And we keep on building up this next task, right? And that kind of gets into the number 2 point of this idea of embodied AI, right? We're seeing more and more in all the models that are being developed today. You can see this in LLMs, you can see this in visual AI, that there's not going to really be this one model to rule them all, right? More likely, in all the applications we'll be using in the future, whether it's self-driving cars or other use cases, it's going to be an orchestration of many models working in unison to give you the outputs that you are expecting. A great example, I've talked to some of these automakers who are building these new self-driving cars of the future. And yes, you want to be aware of not hitting the car in front of you. You don't want to hit the pedestrian crossing the street. But there's also other use cases that they're being considered, such as if I point to an object in the distance and I ask my car, hey, what is that? It wants to come back to me and say, hey, that's McDonald's, right? And, blah, 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 blah. In order to do this, we need to empower these embodied AI systems with kind of very basic information, right? Such as normals and potential key point estimations and surface thermal, or all these other informations that previously we needed to have the hardware there for. Now we can actually just use a model to predict just as good as the hardware previously that was thousands of dollars. Now I can just have one big GPU on the car, and it does all these kind of situations, all this information. And this is still only with, what the work we have today, right? So the idea here that I'm trying to get across is that if you're building the engine of car, right? If you want to build a whole new self-driving car, the metaphor here is that RGB-X models are like the very unsexy part of the car, right? It's like the transmission, right? It's like the wheel, or It's going to be the blinker or something like that, right? Hopefully better than the blinker. I like the wheel, right? Where it's not going to be the engine that drives the next models of the future, but it's going to be a part of it that's going to help empower the AI systems of the future. And ultimately, this is going to help a lot when we get to this kind of blended AR, VR, robots in our society, where we kind of need more information, where the same way that I'm able to know how far away I'm sitting from someone, I'm able to judge based on their facial key points. If their face moves in certain ways that maybe they're a little disappointed with what I said, or they're not feeling so good today, or any of these kind of indications that we previously didn't have. Now we're going to be able to have these with these RGB-X models. It's going to help fuel these systems of the future to help make a better, smoother, and just giving models of the future more information to make more accurate inferences. So it's really exciting to see this kind of development in the visual AI space, because it's exciting to spot them and know, hey, like, I know this isn't the most interesting article. It's not going to have the coolest results or the flashiest demos. But you know that it's building towards something greater, right? That we're moving towards. And so when the next big robot drop or next big VLM comes out and it's incorporating these inside of them, you can spot and say, hey, well, I know the RGB-X models are helping drive these AI systems of the future. So if you do want to try, taking the first step towards those models of the future, be sure to check out our monocular depth estimation with 51, where in a single picture, you can use a depth model to get a depth estimation of how far away everything is in that picture. As well, if you want to find out more information, stay up to date with tutorials, workshops, and other cool models that are coming out in the field today, feel free to connect with me on LinkedIn. Consistently posting models, tutorials, and other things and goodies about visual AI that are coming out. So if you are interested in staying up to date, feel free to shoot me a connect, and I will connect with everyone on this call. I'm happy to answer any questions about RGB-X models or any other things that are related, and I'll be checking through my Q&A right now. So if you have any more, feel free to drop them in. So one person asks, hey, Dan, if fourth channel is LiDAR, is it more sparse than the RGB resolution usually? Have you seen this in use? Are there data or model considerations you can mention about handling this sparse fourth channel case? That's a great question, David. So a way to think about it is, if LiDAR is like on a phone, right, with a picture, my phone in one way or another is doing a depth estimation on my picture, right? The phone knows how far away things are and such. And so in that case, it's probably going to overlay it on a RGB image for whatever the downstream use cases are. Now, if you think about a case like self-driving cars, the LiDAR sensor is probably much more robust, right? It's going to be a 360 sensor that's sitting on top of the car, and it's no longer lined up with an image. So we can still build these cases in the future, right? Using any type of autoencoder, embedding system, pushing everything to a latent space, essentially, you can blend any type of modality, right? So it's more about the application you're using and are these sensors available, right? If the sensor is available, you have to find a new way to incorporate it that matches whatever your use case is. If your use case is you only have a camera, or you only have a camera that doesn't maybe have the best LiDAR sensor or something like that, you're using models to help bolster those for whatever the downstream case is, right? So have I ever seen this sparse fourth channel case? I have seen cases where the fourth channel's dimensions don't necessarily match the RGB image's dimensions. Sometimes they're much bigger, sometimes they're much smaller. A classic example is like a semantic segmentation of the satellite imagery. I don't need to have 40,000 pixels of semantic segmentation. Usually maybe 1,000 by 1,000 does a good enough job, and I'll just kind of abstract that larger out to the satellite imagery, right? Same thing you can do vice versa. If you have a really strong camera with a LiDAR sensor on it, maybe that LiDAR sensor is much more robust than the picture that's being captured, right? It really just depends on your use case, but it's definitely plausible. One more question we get: when building the model while feeding in more information, is there a general concern for overfitting the model and straying away from generalization? With imaging, I used to believe that more data is better to train the model. So in this case, would more information refer to more data in the context, please? Secondly, on that note, would it be correct to see the X and RGB-X models as different channels in a CNN model? That's a great question. So a lot of this type of trainings, and I highly suggest, like, if you're interested in this topic, read the Sapiens paper. They have some insane work in this specific question space where now models are so sophisticated that before we even get to training the model, we're training the model to do all these tasks before we even get to the task we're interested in, right? For instance, Sapiens trained the model beforehand to mask out parts of an image and then infer what they think that image is, like to fill in the blanks, right? And it got to the point where they could cover 75% of the image, randomly mask out pixels, 75% of them, and the pre-trained backbone of Sapiens could then predict what the other 75% that was missing, and with very high accuracy, reconstruct an image, right? Similar to how you would see diffusion models reconstruct noise, right? Not quite similar, but pretty similar. So the correct answer here is when, especially as we get larger and larger into these larger models and complex use cases with many multimodalities, pre-training becomes super important, and how you choose to pre-train to make sure you have exactly what you're saying. You're not overfitting. You're teaching the model novel things. It's getting a better understanding of the context of the world becomes more and more important, right? And then the last question, is the X going to always be an extra channel in the CNN model? Traditionally, yes, that would be true. Nowadays, there's so many interesting architectures about how they handle these use cases. I can go back on a couple slides here. If you see from the RGB-X tracker, this was a CVPR paper from June 2024. They actually took the extra embeddings, they took the extra channel and pushed them into an embedding space first. This way, I could not rely on having every single modality there. If you go the CNN route and you say, hey, expect to have event data, thermal data, and expect to have depth data, well, if one of those was missing, then you would fail, like the model would fail, right? Or would have to keep switching the models out. By pushing them to an embedding space, which you can standardize using some kind of latent space, you don't no longer have to have every single channel there on input, right? You can have this flexibility, and a lot of the field is moving much more towards flexibility, right? I might not have every sensor, I might not need every sensor, right? Can I be ready for that case? Great question, though.